Howdy, I'm back again. Assuming my iPad will stay properly oriented, I'll try and go over another one of these problems. Okay, so we're doing more current density stuff. We want to look kind of at a boundary condition problem. I wouldn't say necessarily boundary conditions in the same sense of like an initial value problem with differential equations, but more we need to consider the fact that there is a boundary within our non-uniform media that we are trying to evaluate, right? So we have two separate pieces of dielectric media here, right? And we know that our electric fields 1 and 2 are moving through this particular media down, and we're assuming that there's an applied voltage here of quantity V. The whole thing is grounded, right? So we have a proper circuit. So once again, we assume that it's V. I already have that written down, beat myself to the punch. But then we also, once again, make the same assumption about the movement, beat myself to the punch again. But as a consequence, because of Ohm's law, we're making the assumption that this is an ohmic material and that the electric fields and the current densities are constant. Then we know that the current densities are also moving at the same direction as our electric fields, right? So now we know that for a fact with a constant parameter at play, we know that we can use Ohm's law, right? So whenever we are applying our boundary conditions, we have to make a distinction though, and that is because we have some sort of boundary here, surface charge will unevenly accumulate on either sides of these things because these have different permeabilities, or permittivities, I'm sorry. This one has one of epsilon 1, this one has one of epsilon 2, right? So just so they correspond properly, you know. So we can't just say that the displacement vectors for either of these two guys, as related to the electric field whenever we're applying some sort of charge to our system, are equal at that particular boundary. Instead, we have to consider the total free charge, which is just the difference between the displacement vectors at this particular boundary, right? So in order to do so, we'll take our difference between those two displacement vectors, which will just be equal to our second electric field times its permittivity minus the first electric field minus its, or multiplied by its permittivity, right? So epsilon 2 E2 minus epsilon 1 E1 at that point there. Consequently, we know that because our current density has to be constant, then our current densities, these two guys, have to also be equal to each other. So we know that our expanded expression via Ohm's law for our current density for the second electric field and its conductivity has to be equal to the conductivity and the electric field of the first bit of our material, or our media, right? So now that we know that, we can begin to look for things like our potential, which will then soon lead us to getting a proper expression for our resistance. Let me move my textbook here so maybe you guys have a little bit better room and I can actually turn away instead of, you know, I can talk to the camera when I'm trying to refer to something, right? So once we have that, we take our standard integral relating the potential to our electric field like we did in the previous example, except because we have two separate electric fields and we want the total potential in between here and here, we need to split that integral up into two pieces, namely for the first electric field and for the second electric field. I just went on ahead and did the liberty of flipping the boundaries of integration and replacing the infinity with the 0 because we don't care about at infinity right now, we just care about the small intervals in which these two guys are moving. I'm taking the liberty to do that. Is it mathematically sound? I guess. In theory, I suppose, but besides the point, this is physics, not math. So once we have that particular parameterization down, we do the integral. We get that our potential is equal to the product of the sums of our electric fields and the distance, or rather the thickness of our media, right? And then once we have that, then we can begin to relate our electric fields to one another because it's not really useful to operate in terms of a bunch of unknowns. So what we do is that we just solve these two electric fields essentially simultaneously in terms of one another, right? Or more specifically, when we substitute one in for the other one, we can get an expression for our first our first electric field in terms of the distances that it's traveling over and the different conductivities of these materials. And then we repeat that process for the second electric field, just making a similar substitution, right? Now, once we have our expressions for our electric fields, what we do is that we can plug it back into our definition for our free surface charge, right? And that's just the difference between the electric fields and their respective permittivities. And after some algebra and after doing some substitution and getting it strictly in terms of the permittivities and the conductivities and the potential, we get a final expression for our surface charge being that monstrosity of a fraction over there. Now, what this basically means is that the charges in between, or the surface charges between these two media, are going to differ by that exact amount, right? So that's useful to know, but what we're also really interested in is the resistance. That's the big question that I posed at the top of the board. What the heck is the resistance, right? NIFA gives us the equation for resistance pretty flippantly, and all we have to do as mathematicians or as physicists is to do some simple algebra, basically, right? So we know that the resistance can be expressed as a ratio between the potential and the product between the magnitude of the current density times the current, A, I believe that's the current. I don't know what else it would be, frankly. Yeah, if I'm wrong about that, I'll double check myself, and I'll put a comment down below if A is not the current, because usually you can represent A with amps, you know. So I don't think that would be surface area. I think that'd be pretty silly. Big A. I'm looking at NIFA. Looking at NIFA right now. I don't believe that's the area A. Until I can see otherwise, I'm just going to assume. Oh wait, yeah. No, that is a cross-sectional area. Never mind. Equation 7.14 is a cross-sectional area. So good thing I corrected myself when I got that term corrected. So our resistance is just the ratio between the potential and the product between the magnitude of the current density and the cross-sectional area. And then all we have to do is just substitute one of our electric field terms and its respective conductivity per Ohm's law, and we are able to write these two guys as equivalent expressions because of the continuity condition we placed on it earlier. So when we do that, we do some wacky algebra, and we're able to get a final expression for our, oh goodness, my Newton's cradle. I need to move that. We're able to get a final expression that neatly packs all of our terms together with just the conductivity and the distance that the electric fields travel. Namely, this one will be sigma C1 times T2 being this distance the electric field or the second electric field travels times the conductivity of the second electric field and the distance the first electric field travels. And then we have a product of the two conductivities multiplied by the cross-sectional area of our system here. So, namely, I think this particular cross-sectional area is the area through which, just which the current flows itself. So it would be like this guy times whatever width is this way, or it might be even this times this. It's an area, but yeah. More generally speaking, just so we have it, resistance is also given just simply as R is equal to 1 over sigma C I of whatever media you have times the cross-sectional area, A, right? So that's how you would find our resistance for this particular geometry, if you want to call it that. all we did was that we looked at how free charge would affect the continuity of our electric field and our current densities. And then once we realized we're dealing with ohmic materials, we have to employ the continuity condition of the current densities, and that allowed us to make the algebraic substitutions when solving for the magnitudes of the electric fields in this particular non-uniform media. And then ultimately we were able to use a simple expression for the resistance that NIFA just kind of hands to us, and we're able to make a substitution and solve for said resistance.